Welcome everybody. Thank you for coming on this very last day of the Game Industry Conference to finding the right networking topology for your multiplayer game. I'm Tim. I work at Photon Engine as a producer and software engineer. And today we will be exploring the different technologies that exist for real-time multiplayer and what the impact is on the topology you might want to use depending on your gameplay. So, what we are asking us today is a question I get quite a lot, is what is the best solution for multiplayer games? Now, as you might guess, the best solution is vague because depending on who is asking, if it's a producer, it might be, okay, what is the cheapest, what is the most cost-effective, what is the thing that my team will integrate the fastest? If it's a programmer, they might come and actually mean, okay, what's the best performance? What is the thing that I can integrate with our existing tools the fastest? If it's a designer, it will probably be more akin to, okay, which solution is the one that will enable me to make with the levels, the abilities, or the gameplay in general in the easiest fashion, which obviously means it is dependent, but in essence, when you look at your game, the best is the intersection of what allows you for the development to make it quicker and more easily, of course the cost both for development and maintenance, and ultimately the player experience, because let's face it, that's who we are catering to. So the answer is, again, it depends, but what exactly does it depend on when you choose your original technology to work with, because it is a long-term commitment throughout the development process? Well, it is in the gameplay. The different factors that you need to consider before choosing your technology is, okay, first of all, what kind of game are you making, the game type? Also, for programmers, what is the information that all the players need to know about the current game state? Also, in terms of design and everything, you need to know how many players will there be concurrently in one game match or session. Obviously, on the other hand, if you go more into the actual end user aspect, you have to consider, okay, what platform is it? So what kind of performance overhead are we looking at? And also, most importantly, for multiplayer games, the platform, what therefore are the limitations for the bandwidth? This is a particularly important point if you decide to go mobile. Even more so if you go mobile in countries like the Philippines or Brazil, where that can be spotty at times. Obviously, ultimately also to prevent cheating down the road, you have to consider who and what is the authority of what is happening in a game, what validates it, what says, okay, this action has happened or it did not happen. And that all boils down afterwards, of course, to the overall cost that you will have to keeping that technology for your game. They're both pros and cons, which we will go over in a later slide. So, but before we go into that, there is something I would like to just refresh the mind of, especially for the non-programmers here, about what it means to develop for multiplayer. And this is what we think of when we look at the internet. It's neat, it's data, it goes from point A to point B, it's clean. That's very sci-fi. The truth is, the internet is more like that. It's a bunch of hardware cables lying all around the world, and that means this is an analog infrastructure, which means even if you send data from one point of the globe to another, there are constraints that regardless of what technology you choose, you will always face. The most obvious one is latency, because the data cannot be transferred faster than the speed of light. So latency is something that regardless of what you do, you will always have. Therefore, the solution for latency here is not something that is a technological problem, but it is something that you have to consider in your sound design, in your gameplay design, in your animation design, in order to afford the data, the time it needs to transfer between the servers and the players. Also, since this is a physical network, there is obviously fluctuation of how the data is received, whether it's in errors or whether there's what we call packet loss, meaning data that's not arriving. And these are things that are, for the larger part, solved in the technologies and by your programmers thanks to error correction. So, and that brings us to the second point, time complexity. Because as we mentioned before, latency is not going away. And therefore, time exists in two ways in multiplayer games, the measured time and the perceived time. Specifically, that means the measured time is subjective. It is, in short, what your player will see. It is also subjective to each machine that is connected to your network. This means, regardless of what you do, time will never be identical in any of the simulations that you run. This is one of the biggest headaches in computer science to this day. Time across time zones in particular, but also from a purely programmatical and hardware perspective. So if you rely in your multiplayer game on time that is perceived by one machine, you are going to have a bad time. That is unavoidable, unfortunately. And more specifically, to solve this problem, instead of counting time in the sense of seconds, minutes, or whatever other fixed measurement you have from a subjective point of view, you want it in a discrete measurement, or in this case, we refer to them as ticks. Ticks are very simply the update rate of your simulation. So just like for rendering, you have 30 FPS, 60 FPS, 120 FPS, you can also say that your simulation runs at a fixed update rate. This is very common, for instance, in physics simulation, but just applies as much here in multiplayer games. Now, for perceived time, there is one solution, and one solution that your programmers have already come across, and that requires this whole tick-based system, and this is what we call predict rollback. As I previously mentioned, time is subjective to the different machines because of their location in comparison to where the data is being sent and received from. This is, as we mentioned, referred to as latency. And of course, this latency can then be translated in more or less the discrete measurement of ticks that we have per machine. This means in order to give the player an impression that everything is happening at the moment that they're doing things, the local system needs to actually predict the future based on the information that it currently has. But because of the time it takes the information to go from the server over to each client, of course this information is technically speaking old. And therefore, every time it gets the confirmation, okay, this was the actual game state or the input of a player at that exact point in time of the simulation, so at this specific tick number, the simulation needs to basically roll back the state of the game, meaning go back in time, and then resimulate each step until it has reached its local time, that is the perceived time of the player. This is something that can only be done if you have a simulation that runs based on ticks. If you do have it in the measurement of a simple machine in terms of units of time, such as seconds or minutes, this is not going to work. But okay, let's go now into the actual meat of this presentation, and that is the technologies that we can use. Technologies and the concepts for multiplayer have pretty much been established already 30 years ago. There are two types, state transfer and determinism. State transfer is the most common one used because it's the most simple conceptually to see, whereas determinism goes a bit more complicated from a conceptual point, but tends to be a lot easier to use down the road. And to be specific, state transfer and determinism are actually state synchronization and input synchronization. What that exactly means, we will see in All right, so as I was saying, let's talk about state transfer. So, state transfer has been around for a very long time. We have already in the 90s with games like Quake seen this technology used to great efficiency, and it has only evolved since to be used in pretty much any type of game at any type of player count up to today. So we had, of course, Counter-Strike, typical example from the early 2000s, going all the way to now games like Warzone with 260 players, or Fall Guys physics simulation with 60, or of course, smaller games even like Valheim that only has 10. Now, all of them use the performance offered here to reach their player numbers and the gameplay. How exactly is what we will be investigating right now. So, first of all, as the name implies, state transfer means that you are transferring, well, the state of the game. Now, the important part here is to keep in mind that you don't need all of the data transferred, because when you develop your game, a lot of the information is actually just visual. So the state of the game is just the information that cannot be seen by the clients. This is, of course, then compressed and sent as a one snapshot over to all the clients. They then replicate that into the local objects in order to have the same state as the server and correct it if necessary. Now, as you can imagine, a game state can grow a lot. And there is one limiting factor. Well, it's not necessarily limiting, but we will see why it should be. And that is the so-called MTU, or the maximum transmission units. It is the maximum size that a transfer protocol such as IPv4 or IPv6 will support. In the case of IPv6, the definition is 1,280 bytes. Now, this is the theoretical maximum size of the data packet you can send between the server and the client in one singular transmission. This is important to take into account when you optimize your game and your game state, because the bigger your state, the more into more packets it will have to be split. And computers can only recreate a whole state if they get all chunks from a singular data packet. If they do not, they will simply discard all of it, which means the server has to resend it, which creates more latency and eventually a worse experience for the player. In addition, there is a practical maximal size, because as you can imagine, it's not just data that's in this packet. It needs some information about actually who it's sending to. So all of these default things are things that you will find regardless of whether you're sending information for a game or not. But in addition to a game, you will have some metadata about, for instance, which tick number, etc. And so the actual size of your game state needs to be well below these 1,280 bytes. Now, of course, this is inconvenient, to say the least. Therefore, there is something else that can still be done, and that is called delta compression. As you can guess, your game does not change all the time, or more importantly, not all aspects of your game change all the time. Therefore, in order to compress your state, what you actually want to include in this packet is only the changes that have happened since the last packet that has been sent. This will reduce the size of the information that needs to be sent, and therefore you can send effectively more information and have a bigger game state, since not everything needs to be updated for everybody all the time. Now, this is of course different if somebody is joining your game after it has started. It will have to receive the whole game state, but that is another topic. Of course, now we have talked about the state, but you might wonder, what happens if we have too many players, or even just too many units of any kind? What else can we do? Well, eventual consistency. Contrary to delta snapshots, or snapshots in general, eventual consistency transfers only the data that is of interest to the player around them. So that could be, for instance, what's in their view, or simply what is in a given circle around them, depending on your camera view or the other calling methods that you use. Now, eventual consistency is definitely what you will want to have for games such as Battle Royale games or large action RPGs or MMORPGs, of course. What it does, as mentioned before, is it just looks at the area of interest. So where is the player? What are the objects that the player, or more importantly, the client, so the computer of the player, cares about in order to provide the experience, and include only and only that into the snapshot. Everything else is ignored as far as that particular player is concerned. This allows us to have, of course, higher performance, which is the goal, especially in high tick rate, high fidelity simulations nowadays. And the important part here, as you see, is the bandwidth. We have up and down. And this is the part that tends to be forgotten, because the connection of the average player is just your consumer bandwidth, which has, over the last couple decades, been optimized for downstream. So downloading a video, watching Netflix, and even downloading a game. And therefore, if they play with a server, fantastic. But they have usually a much more unstable and less efficient upstream, which is what you usually need if you host your server somewhere else. That is why these commercial connections, especially in the late 2000s, you had some semi-successful games that just had a desktop computer on a business connection in their office, and that was perfectly fine because they had a good upstream and therefore could send the data to all the players per second that was needed. But enough about state transfer. Let's see at its competitor, determinism, or, as I mentioned, input synchronization. First of all, let's see what determinism actually is about. According to, well, the Wikipedia definition, it is the philosophical view that all events are determined completely by previously existing causes. Or in layman's term, one action has exactly and only exactly one reaction. That means as long as you're aware of everything that has happened in the game, you can execute exactly the same action on all the machines without synchronizing any additional data. Now, this is really convenient because the only thing that the developer cannot control in a game, especially a multiplayer game, is the player input. Everything else is known and are things that will only exist in the simulation itself and are not player introduced. That means when you have a deterministic simulation where everything is deterministic, the only thing that you as a developer have to care about is input. And that is really convenient when your team does not have any netcode experience, which means any gameplay programmer can code your multiplayer game because it works with input and just like anything else that they have coded for single players so far. However, it comes, of course, with a different type of difficulty. Because it has to be deterministic, it has to have a simulation that is completely independent and isolated from anything that is, well, not deterministic. And usually that means your view being your animations, your VFX, your sound, and anything else that you usually would have, for instance, in the engine. Those are usually not things that are important for the simulation itself or the behaviors. This, of course, in today's modern structure, is the most conveniently done by having that inputs sent to a server that knows of the update rate of the clients, validated, timestamped, and then batch forwarded to everybody. Once that input has then arrived, all clients can, as we saw before, do a rollback to the state that they just received and then resimulate what the actual state is for all the clients without actually having to transfer any other kind of data. But, of course, as I mentioned, it comes with limitations, or rather opportunities, depending on how you look at it. And that is, a deterministic simulation has to be, as I mentioned, fully deterministic. That means no floating points, That means no external factors that are not cross-platform compatible if you decide to have mobile against PC. It means that anything that touches the simulation part of your game has to be fully deterministic. Your math, your animation controls, your physics, your pathfinding, and even, of course, your ECS system, if that's what you're using. On the other hand, anything that is unrelated to the simulation can be based on whatever you want. So the input can be any type of controller, mouse, or keyboard. And of course, the network transport layer is just that, a network transport layer. Which brings us to the next point, and is really important before we move on to the second one after that. That is, in all of the graphics that you have seen so far, there were peer-to-peer connections. But peer-to-peer, as it's been popularized in the 90s and the 2000s, is dead. And yet it's still alive. What exactly do I mean by that? And why it is important for you to know is because the term tends to be misused for different concepts. True peer-to-peer requires every computer in your network to communicate with every other computer. This means for any player that joins, you have the amount of players times the bandwidth that you need that grows. This is a huge problem because there are actually traffic jams on the internet, simply speaking. This means while you as a developer don't have to care, it means that there is a possible delay at every single connection with every single computer, which will lead to very easily a desynchronization of the game state and all other potential issues. So with this taking into account, in the late 2000s, a much more preferable architecture emerged, which is the client-server structure. This is, technically speaking, also peer-to-peer because it connects from, well, one peer to another. The difference is that all peers connect to one single master peer, essentially. What you have probably used at some point or another is, for instance, a dedicated server running a headless simulation. This is used a lot in competitive games, for instance. For those of you who don't want to have the overhead of a dedicated server, you can use the client host, which is simply one of the players that has also a small server simulation on their end, and therefore only their upstream bandwidth will grow whenever a player joins. However, it grows one per player instead of having a squared growth, which is very convenient. And that brings us to topologies. Topologies are the network architecture, essentially, that you can use for each of these technologies. They have cost implications, but also they have simulation authority implication. And depending on the kind of game that you build, this is important to consider. If we first of all look at state transfer, which, as I mentioned before, is the most common one to see, you have three types of authorities and topologies available to you. The first one, and that is probably the most known one, is the dedicated server. This can run, for instance, again, a headless simulation on a dedicated server. So if you take Unity, for instance, it would just build it out, but without any of the graphics and any of, well, the viewport that the player would usually have. This requires, in addition to just your simulation, of course, to spin up every dedicated server when a new match starts. That's why usually you want to have a server orchestration system behind, such as, for instance, GameEye or PlayFab, in addition to what you already have, such as, of course, on your side, matchmaking, and so on. We will come to the symbols in 1 minute. This is, again, very convenient if you need a singular instance that has a say over everything, your server, but it's costly. The alternative is the host mode or client host, as mentioned before, where you cut out the server orchestration and the dedicated server simulation and simply have one of the players host it. This opens the door to some, well, player cheating, since the simulation is on a PC that the players have access to. You can't segregate them from it. And finally, we have the shared mode or shared authority. This is, well, used to be very popular and still is today, where basically every client, every player has a say over what happened from their point of view. This is very convenient because that means they see immediately the actions that were taken, but you as a developer have very little control about whether or not that behavior was actually intended or even should have been restricted to begin with. On the other hand, if we now go to determinism, well, you don't really have that issue because, again, the only thing that you synchronize is input. Every player has an exact copy of the simulation at any point in time. And if somebody decides to modify their perceived simulation, it will not affect any other player except for themselves. And therefore, it is, to at least the most common ways of cheating, impervious to it. Now, if we put them all next to one another, as I mentioned, there are different pros and cons for each of them. The first one, and that what we already addressed, is the authority. The dedicated server one is the one where the authority is clear and is very strong because the players don't have access to any of it. The hosted simulation, you can put in checks, but of course, you don't have control over the system it runs on. And the shared one, well, I mean, all bets are off here. When you come to the game state, there's something you have to take into account, and that is host migration. If a player drops out of your game, what happens to the game state? Who runs the game? Who has the authority to tell what it is? And what happens to all the other players that were connected to it? Now, if you have a dedicated server, well, either your server is up or it's down. That's that easy. When it's a client-host one, most technologies will keep a snapshot of the state that will allow any player to take over and basically become the new host. This can, of course, work fairly easily, but you have still the same problem that you don't control which devices it ends up on. And if you have a cross-platform title that goes on Switch or mobile or PC, then you might end up with somebody that's on a different type of connection that you hadn't optimized for, and that makes it a bad experience for everybody else involved. In the shared authority, well, everybody has the full game state, so that's taken care of. In determinism, you don't care because the simulation is always the same regardless of who is here or who is not. The same applies to latency. Dedicated servers, you can host them close to your player base. You can host them in a data center that of your choosing, and you control most factors. Well, except again, for whatever the connection is on your player side. Now, for the host one, as we already mentioned several times, it is completely dependent on whoever is actually hosting the game. Or worst case, if somebody cannot directly connect to the host and has to go through a relay server, that will be even more delayed. But that's usually about 10% of your players at most, so not a big concern. For shared one, you have direct connections, but again, since every player has the authority to decide what actually happened in the game, if a player has a bad connection to the others, that means that they will receive a very old decision potentially further in time, and that will impede the experience of all other players. In determinism, you don't really have that issue since you can decide that the master server that synchronizes the inputs just times out players, or rather, times out inputs for players whose input hasn't reached the server in time. So the only person affected is whoever is having the bad connection, and everybody else just continues playing their game as if nothing had happened. So then, of course, we can talk about the quality of service, but that is pretty much the same as we have already discussed. And that brings us to the last point, which is cost. Now, dedicated servers can be expensive for two reasons. You have the server orchestration and you have the CPU time of your actual dedicated servers. And computing time, especially on servers, is expensive regardless of what you do. You can have the hosted mode, which is pretty much the same as a dedicated server, except it's hosted by players, which means from a code-based perspective, you don't have to change anything, and it is more affordable since you don't have to host a dedicated servers. Shared mode, you don't host anything either, but all the players do. And determinism, nobody hosts anything since the simulation is identical on all the clients. Which brings us to another topic, scalability. And this one is particularly important because there are two very distinctive factors to take into account to evaluate that properly, which is on one hand, of course, cost, but the other one is capacity. First of all, the cost. If you run a multiplayer game, the cost that you have is how many players are concurrently connected to your system playing a game on whichever topology you have. Concurrently meaning how many are connected at a singular point in time together. It's not about the amount of daily active users, it's not about the amount of monthly active users. And this is very important to understand because most people tend to overestimate the amount of CCUs, as we call them, that will be used at launch or even at the tail end of their game. To give you an example, over the last 2 decades that we have been operating, we have come to the rule of thumb that we call 20x. On average, you have 20 times the amount of daily users that you have CCUs and 20 times the amount of monthly users that you have daily users. Which means if you were, for instance, to have an infrastructure that supports a concurrent amount of 1,000 players, then that would probably be equivalent on the conservative end of 20,000 daily active users and 400,000 monthly active users. That means that your server cost in comparison to the monetization that you have for such a huge player base, even if you have a premium game, will be tremendously low. So if you want to scale properly for your cost, keep in mind it's not the amount of players you have. If in worst case you have 400,000 people active at the same time, that would be absolutely amazing, but we have never seen that yet, that you have an equal amount of copies sold to active users just because, well, there are time zones in this world, so nobody's going to be playing at the same time anyhow. And then there's the capacity. And capacity needs to be split, here again, in 2 different things. Number 1 is the actual player count. Now, the player count is typically what you see when a new battle royale comes out and goes, oh, we have 100 players, 150, we have 90, whatever. And this is something that is limited by the bandwidth available to your players. And that is, again, dependent to a large extent on platforms, meaning are they on a home connection or are they on a mobile platform? Now, this is something that is not optimized after release. This is something that is dependent on the optimizations that you have done of your gameplay and therefore of your game state. That is the deciding factor. Depending on how big your game state is, you will be able to transfer more or less to more or less people. Or in the case of determinism, the size of your inputs. Then there is the other aspect, and that is the one that you can scale post-launch, and that is the dedicated servers. Now, the amount of player sessions or matches that you can run on any given server is completely dependent on the server spec and how you run that yourself. And then, in addition to that, you have the server orchestration. So, if a server doesn't have the capacity to run an additional match, how can you decide where to spin up another server? That could also be dependent, for instance, if you have more players in the Asia region than the European region at a given point, or in the US rather than in Africa. And this is all things that you can do, of course, post-launch. And that scales with how many players you have. Therefore, the cost will as well. So, let's get back to the original question. What is the best solution? As you guess, again, it depends. The best solution depends on identifying, first of all, what is your major gameplay concern? Is it the player count? Is it the authority because you have a competitive game? Is it the amount of units because you have an RTS? And what is the technical solution that is attempting to solve specifically your biggest concern for gameplay? Any solution you choose has its own drawbacks. But the important part is what is the focal point of your gameplay experience, and that will be the deciding factor, because you will have to do work regardless, but it is better for you, obviously, both in terms of fun and also less overtime, to work with a technology that goes hand in hand towards the player experience that you are aiming for, rather than one that is designed for something else. Here we have a nice little graph that summarizes, roughly speaking, the different types of games and which topology works best for them. If we just take now FPS games, for instance, which are high-paced and have all possible platforms they run on, these are one of the edge cases that technically could run on any of these topologies. However, it depends again on the gameplay. If you take a competitive game like Valorant, Apex Legends, or Counter-Strike, if you have ranked matches, these need to be run on a dedicated server because, again, you want to have full authority over what has happened and give out rewards based on that. In addition, if you take, well, Apex Legends in that case, there are so many players that you cannot possibly transfer the whole game at any point in time to all the players. That would just explode your bandwidth, and that is a tremendous cost as well eventually. So in this case, you also can use eventual consistency with areas of interest to segment the data that you send to any given player. On the other hand, if you do a co-op FPS, like your Borderlands, your Halo, your Left 4 Dead, your Portal, you can have that on a client host. This is a game that has only social aspects to it. Whether somebody messes with the simulation or not is not going to affect anybody else on your player base. So why not? You can even host both this dedicated server and the client host topology together. Since it's the same code base, you could have ranked matches, for instance, run on dedicated servers, and then community matches run on client host, which is, for instance, what you see on Counter-Strike. You can go, if you go on the community list, scroll down and see what's the ping to which server, if it's been modded, if it's not, because that's fine. It's a community match. Alternatively, of course, you can use a shared topology if it's really just a bigger map and you want each player to kind of be able to tell, oh, this happened on this part of the map. So that is definitely an option. On the other hand, if you were doing an FPS on mobile, depending on the pace of your FPS, you might as well use determinism because, again, it's not as fast-paced as the others, so you don't have to have, for instance, the same type of lag compensation, but you have a bigger issue with bandwidth and packet drops because, well, depending on where you are in your house, for instance, well, your connection might just drop out because there's a wall, there's a water line there that you didn't have just 10 seconds ago, and therefore you don't want to deal with that. Of course, there's some game types that are just very clear contenders for one type of topology over another. And two of my favorite examples for that are fighting games and RTSs. These are games that have always run on determinism, at least the ones that have had good reviews. Age of Empires 2 is the oldest example of that, of course. In fighting games, if you look at the reviews for any of the, well, for instance, Smash games, the issue that is always mentioned is that it's not predict rollback, it's not deterministic, and it's essentially a problem also for competitions in that case. On the other hand, if you go with games such as Among Us that are a bit more casual on mobile, you can go definitely with a shared mode since there is no high-level stake as such. Or if you have a physics game that is very dependent on where players are, then you could host that in dedicated mode. And then a final thought that I'd like to share with you. Single player or multiplayer, which is a question we get often. And the truth is, today, it is not either, but both. And the reason for that is very similar to the design philosophy that has emerged in web design about a decade ago. You should always design both from a programming perspective as well as from a pure gameplay design perspective for whichever device is the most constrained that you want to support. In terms of websites, that used to be mobile, and a responsive mobile website would work on tablets as well as on PC. And the same is true here nowadays for games. If you build your game with multiplayer in mind, you will have mechanics and systems that do work in an offline scenario as well, because the constraints for multiplayer as to how you have to segregate your data and the patterns that you have to use for both your gameplay systems as well as for your view are much more stringent than what you will have to do in single player. This is also further enabled by the fact that most technologies nowadays allow you to do one code base for both. And therefore, you can basically develop your game with multiplayer in mind, and once it launches, decide whether or not you actually want to have the online pipe run. Because a single player is conceptually a multiplayer game of one person. However, a single player game cannot have multiple people, because otherwise, well, it wouldn't be a single player game anymore. But enough of that. If you have more interest in, well, networking in general and multiplayer games, these are a couple of books I can definitely recommend to you. Multiplayer Game Programming by Joshua Glada and Sanjay Madhav is very popular. And also the whole series by No Box Hair. Those are all available as ebooks as well as print, and give you definitely a lot more insights into the matter if you so desire. Questions? So I'm aware of Network Next, but these are strategic questions that I'm not involved in, so I don't have an answer for you. I'm sorry.
I got two questions, actually. The first one is about security. You mentioned that, well, if you have a server, it's the most secure solution, if I understood correctly at least. But, well, sometimes in co-op games, we don't need a server, but we still, well, since the games can be broken, we need some layer of security still. Do you have any do's and don'ts when, well, how to make these games less easy to break, maybe?
All right, so this is a question that unfortunately is very dependent on your gameplay. I agree with you. If you just have a co-op game, there is little reason to have a dedicated server unless you go into the whole, crypto and NFT space where you have real money involved. One solution, if you don't want to run a full server simulation, could be that you have a server plugin at the relay level that validates actions from the players. This is something that can always be done post-game release, since that is not connected to your own code base, but is happening on the relay server directly. Definitely an option. But again, I think the main question you have to ask yourself as a developer in that case is, if this is a co-op experience that only matters for the people playing it, do you care? Because any additional security layer that you add, while possible, is always going to involve higher costs.
And the second question is, there is a solution called Mirror, which claims to be alternative to Photon. Have you heard about it, and what's your take on it?
So, well, Mirror has been around for quite a while. It's evolved from UNet originally, and it is based on message synchronization rather than real-time tick-based simulations. So it has its use cases, but it really, again, depends on what your gameplay is. That is the only take I can really share with you at this point in time, because that is so heavily dependent on your own vision that anything beyond that is too subjective.
Okay, thank you very much.
Yes, of course.
So maybe I have another question. Probably I decide to go with Photon with my game, but the main problem, if you're creating a game that is not the sport game and you want to allow the players to host the game, and for instance, in my case, I want the host to be dynamic. So if the person who is responsible for hosting the game can leave the game and it still should run, and just another player should take this role because it's just only a logic part of the gameplay that is synchronized by this one person, or just forwarding the inputs from other players. Um, the main problem is, of course, port forwarding, allowing the player. No, every player have like can forward the port on the router and so on. If Photon provides this possibility, like for example, the Steam API let me like connect people through the Steam servers, and it like eliminates this problem of reaching the host by another player if Photon provides the same solution.
All right, let me split that into two different questions. Like one, like yes, sure that we offer that, but the information that we showed here today is applicable to really any networking technology. So your question has two, like yes, business, yes, we do. But from a technological point of view, so the net punch through for the direct connection, that is something that is handled by whichever service you use. So if you use a Steam API, you do have to handle that yourself, which can be a headache, which is why most of the time you need, and it has to do with the networking addresses on the local and public network. I'm not going to get into that. But as far as host migration is concerned, this depends very much on which technology you use, and will then allow you to decide whether it's possible or not. If you use a topology such as client server, then since the game state is present as a whole somewhere, it can be migrated to another player. If you use a shared topology, it is technically possible, but will require work on your part because the game state is changed by each player, and this is not something that can be standardized. If you have a deterministic simulation and use that as a topology, then there doesn't need to be a host migration in the first place, since, again, all the players are aware of the full simulation at any point in time. So I hope that answers your question.
It's more like
Right, I think they would like everybody else to hear as well.
okay. I asked more like providing the external room for players to communicate with each other, to like eliminate the problem of using the open NAT, for example.
In that case, you're looking at dedicated servers.
Yeah, and the only question was that is Photon providing the possibility to manage the dynamically changing host who have like authority over these rooms that we can spawn for a game.
So again, this is definitely a business question. We can go into a bit later if you want, but generally speaking, the answer is yes.
Okay, so thank you.
All right then. Thank you everybody for attending, and I wish you all a good Sunday until next year.